Hi, this video we're gonna talk about the property of an area known as second moment of area, and it's known as a symbol I. So moment of area is important property that give us information, tells us how hard it is to bend something. That's it. How hard it is to bend something. Now let's look at some simple example here. You have this ruler. You realize it's very easy to bend along this direction, which is right here, right? Very easy to bend. Where you're bending away from, what's your bending axis? If I were trying to draw, you have this thin thickness here, so that's your bending axis. You're bending around this axis. If I zoom out, if I'm trying to make it a little bit exaggerating, so this is going to be the ruler, and the bending axis is in this grain. And you realize there's a very tiny little area distributed away from both top and bottom, right? Very limited amount of area away from the top or bottom axis. Now let's look at another scenario. When you are bending this way, it's really difficult to bend, right? And so if you look at the cross section, what you are looking at, this is going to be way bigger because I'm bending this way. And it's nearly not bending. This isn't a bending axis. And when we're trying to bend in that way, there's going to be greater area distributed away from axis, either from top or bottom. So then you start to see it. This second moment of area, this I, tells us how hard it bends to something, has something to do with where our bending axis is. It depends on bending axis. And from this example, you also notice more area distributed away from bending axis, the harder it bends. In other words, if it's harder to bend, then this area moment of inertia increases when there are more area distributed away from bending axis. Now let's look at some other example. If knowing that we have this cross section, if this cross section you're trying to bend, is going to be this rectangle, okay? And if we are trying to bend this, depending on what direction we're bending, if I were trying to bend this regarding this axis, and this has B and H, base and height, or I can flip around, then I have this rectangle this way, and this is our B, this is our H, and I'm bending around this direction. So now I'm bending this way. If I'm trying to bending around that way, of course this one is way easier, and this is gonna be harder to bend. Why is that? Here comes some formula when we're trying to look at different shape. They said for a rectangle, this is going to be the I. They calculate, actually in statics you are going to derive it, and it's equal to 1/12 BH cubed. And this one, the I, let's call this, if it's x-axis, this is called y-axis, so it's ix, and this is y. This is same format. However, the power of 3 is going to be at b instead of h. We know h is way greater than b, right? For this situation, height is greater than base. Therefore, this, when you do h cube, this value is going to be way greater than iy. Therefore, this is going to be harder to bend. And again, you can look at it, the way more area distributed away from this axis. And however, here, you only have very small amount of area distributed away from axis. Okay. And now let's look at another example. When you go to the construction site, you will realize a lot of this beam shape as I, right? They call I-beam. And when you have an I-beam, and the load often is, this is going to be the external load. And if you have load going that way, and consider if you have this beam that's have all those loads going around, so think about what's going to be the configuration of bending. If I would just look at a cross section, and then what bending is going to be, we're bending around this axis, right? Because it's gonna bending around that axis. And notice the area away from this bending axis, either from top or bottom. There's quite a bit of area away from it, right? However, we never really see this beam was in this direction. We never saw any I-beam that's constructed in this direction. So basically, the load is not coming from here. If we're coming from there, thinking about what's going to be the bending axis, where it's bending about, that's going to be here. It's going to be this axis right here. And if you think about this, and do we have a lot of area distributed away from it? Not really. You see here, it's pretty close to the bending axis, and here just a small amount that's away from it. And this certainly first configuration have way more area distributed away, so this is going to be hard to bend. This is going to be easy to bend. Okay, that explains why at the construction site you see the load coming this direction and I-beam is set up in this configuration. All right, okay. Then I'm going to talking about one more concept, is the basic formula to figure out the I. Okay, the basic formula to figure out the I, we can use this example. If this is going to be ZZ axis where this bending about, and this is going to be little area, and the distance here is R, and then they defined this I rotating about or bending around ZZ axis is going to be equal to R square A. Okay, and if you are going to consider this is going to be integration, if you consider this is dA, then this IZZ, you can integrate, it's going to be R squared dA. And that's how we come up with equation for rectangle here. It's all coming from this governing equation, R squared dA. Now let's think about the unit. The unit for mass area moment of inertia is going to be meter to the power of fourth, because you have meter square here, distance, and then A, it's area, it's meter square again, so you got meter to the power of fourth. Okay, so we're talking about the common shape if it's for rectangle. Here is our formula. And it's different depending on what you bend about, right? And now let's look at a circle, another example. If you have a circle, you can bend around this axis. And then let's see, if I flip around, if this is going to be your x-axis, this is going to be your y-axis. What do you think about ix and iy? They're equal, that's right, because regardless, you're going to have the same amount of area distributed away from either x or y. And using this fundamental equation, later on in statics, you will derive the formula for area moment of inertia. It's a half pi r. R is the radius to the fourth. Okay, so those are the two common ones. So here, now let's look at one last example. We're talking about mass moment of inertia. Now we're going to look at the I-beam. For this I-beam, we're talking about it's going to be Ix is going to be way greater than Iy because there are more area distributed away from the bending axis. That's why when we see I-beam at the construction site, they are all in this configuration. Now, knowing Ix is greater than Iy, you can actually look at the example over here in your book. You see this one is always greater than Ix is always greater than Iy. Now, we're talking about those two numbers in I-beam. The first number means 460. That means the depth. It's nominal depth, so it's 460 millimeter. The actual size is 463. You can look at the previous video on nominal versus actual. And so here I want to point it out in this table. It's only focused on this IXX column and IYY column that give us the the tabulated data on this two. Now let's look at let's go away from SI unit, and now let's look at US system. Again, there are two numbers here. The first number is going to give us the nominal depth, so it's 18 depths inch here. However, the actual size is 18.21, and look at this. Look at IXX versus IYY. It's going to be always greater. Again, more area distributed away from it. All right, and if there's a simple problem, they ask you, okay, for 8 by 31 I-beam, how many fold higher? Or what's the ratio between IXX and IYY? So this would be very simple problem, right? You will look at IWA31 and you look at IXS is going to be greater than IYY. The value is given. So here is 110 and here it's 37.1. So that's a ratio. Then you can put in calculator, get your answer. So that's the mass, that's the area moment of inertia. So you realize, a quick recap, it's tell the property how hard it bends, and you realize it depending on the bending axis. If there's more area away from this bending axis, it's gonna be way harder, right? Just think about the yardstick. And then with that, we come up with some common shape like a rectangle cross section, and we know the formula for that. And we also come up with the circle. It's Ix equal to Iy, and then we know how to look up the data from table to look at I-beam, IXX, and IYY. So that's all. I'll see you next time. Bye.